hope you can hear me. Yeah, I think there's a microphone. Yes, so today actually, because this is sort of an ongoing research project that I'm involved with at the moment actually. So this is actually something I started after I left Cambridge and started my lectureship at the University of Kent. And I also would like to sort of highlight that this research, although I didn't really look at the Palace of Westminster during my PhD, but what I've done during my PhD is sort of look at the technical performance of historic buildings using historical materials as a way of learning about buildings. Because there's a different sort of approach. If we look at historic buildings, we might monitor them with modern technology, because we might evaluate them with modern standards in mind. But that not necessarily helps us to understand what the designers at the time were trying to achieve and how well they actually achieved those goals with the technology they had available and the scientific understanding they had at the time. So a building like the House of Parliament, one can't really understand outside the historical context, either in terms of its environmental performance nor the design ideas behind it. They were very much shaped by the scientific understanding, by theories of its own time. I think this is really quite critical. If one wants to evaluate, for instance, the current system in the House of Parliament, it's really quite critical to understand actually what were the original intentions behind it, rather than just reviewing it from a modern perspective without that historical background. So there's a sort of a bit of a history of science perspective I might sort of take in that. And this is a view of the House of Parliament, and I'm not so sure how familiar you are with the building. But the building is known for its being in a Gothic Revival style and the association with Pugin and Barry. That is sort of really the strong image that we have, the picturesque composition of the roof line of the building. But what is quite remarkable of this building is that this building wasn't an exercise in picturesque composition per se. It was actually in some ways an accidental result of scientific experimentation that was going on inside the building. So what you see, the skyline, you might think about the clock tower and the Victoria Tower's architectural features that had already been part of the original competition entry. But in addition to that, you got a number of additional smaller spires that makes this very picturesque skyline of the building. These were introduced retrospectively for ventilation purposes. So they're, in a sense, functional elements that became architectural features during the process. So what is interesting about this building, there's a sort of dialogue between the sort of historicism of the time, so the interest in the Gothic Revival on one side, and the technical advances and the willingness to embrace technical and scientific progress of its time and apply it to a modern building. In this case, a problem of effectively ventilating a large public building that has two major debating chambers inside, are highly crowded and very difficult to manage. So what this building is actually the outcome of an incredibly laborious research and development process. And so if we start peeling away that Gothic Revival face of those towers, we see there's a lot of mechanical systems inside it. And this is actually the North Tower. So if I go back, we have got this tower here, which is actually the exit point for the Houses of Commons. So the hot air was historically extracted from the Houses of Commons through this shaft. This was one of the extraction shafts. And if you look at the historic drawings of that, then you can see there's a lot of intricate mechanical detailing going on inside these shafts. And that was part of the reality. So we got these sort of two things coexisting. For instance, you noticed here there are the intricate wind guards that were introduced in the tower to prevent foul air and smoke to be blown back into the building when it was windy. So this sort of technical climatic understanding was actually embedded in these towers. So they're technically highly sophisticated. And here we get another view, and you can see these various openings that might look a bit like a church tower at first sight, but actually were appropriate to the outlets. In this case, there was at the top you had the smoke outlet, while at the bottom you had originally vitiated air, so the foul air was moving out. And you can see this in the cross-section, the gray area showing the smoke outlet rising to the top, because the smoke was to be exhausted as high as possible to prevent smoke coming back into the building. While the vitiated air was exhausted at a lower level, while it as it didn't have really the noxious fumes associated with it in the same way. And so if we put this into context, I think we need to imagine that the building was actually a collaborative effort. It involved scientists, architects, and engineers. And David and Charles Barry as the chief architect of the project. But we also had one chief scientist who worked with Barry on the project. It was called David Boswell-Reid. Although he was not the only scientist, there was quite a number of scientists involved at different stages of the project, looking at ventilation and climate control. But it was David Reid who has actually been quite involved in sort of critiquing architectural practice at the time. And this quote, I think, sort of, he talks about that actually the design process in the 19th century, where these new technologies were emerging, just a bit like today, there was a process of actually negotiating between the pressures of technology and sciences and the opportunities those brought, and those architectural ends that people tried to achieve at the time. So in this case, there was this awakened interest in the Gothic style and the reawakening of the Gothic revival and the various symbolism that comes with it. But also, at the same time, there was this sort of interest in the technology. And these were both present in the building. And for David Reid, who was really struggling with actually collaborating with the architect, he really sort of emphasized that actually the technical, us really today, very often needs to be really strongly defended against the sort of more formalistic aspiration of the architects. By having that team, there was essentially this push and pull going on between the architect and the scientist. And how could you reconcile basically those utilitarian demands of the ventilation system and those aesthetic demands? And if you remember the first picture I've shown you of the Palace of Westminster with the picturesque facade, the picturesque facade was not the original architectural vision. It was a form that emerged as a system emerged. The original design of the building was rather different. So that is sort of a reflection of that sort of attempt to negotiate between the demands of functional requirements of the ventilation systems, the mechanics of it, with those architectural ideas. So there was a dialogue going on. The sort of form of the building evolved sort of in parallel. And at the same time, Reid as a scientist was not only sort of promoting sort of utilitarian ideas, which of course were quite prominent at the time, but he was also interested in the idea of performance-based design. So for him, it was not enough to just promote ideas of functionalism, but to also test buildings. And I will explain this throughout the talk, how this manifested itself, but I just want to highlight that for him, actually, performance of building was not related to a purely technical matter. So we might think about how these stacks were actually performing mechanically, but he was also thinking about it in terms of environmental conditions inside the building. So you might think about air quality, the relative humidity, the temperature, and how those environmental conditions would affect people physiologically. So we might be thinking about thermal comfort, we're thinking about health. So these are triads. We might talk about technology, environment, and human physiology were rather critical in his approach to performance-based design. And this is not very, in some ways, quite a holistic approach that we find again today in other projects, in modern projects, like Passive House Standard, for instance. There's also this interest in exploring, on one side, sort of technological possibilities of energy efficiency, but on the other side, also the possibility of maintaining a good air quality, of filtered air, and so on. So this sort of that environmental design is not a purely technical subject, but it's also something to do with the air that we breathe and how we feel in the environment, how healthy it makes us. So there was this sort of interest in thermal comfort, health, and the ability to do mental activities inside buildings. And I will explore that in more detail later on. And David Boswell-Reid so when he talked about performance, his idea of performance was strongly influenced by an experimental tradition that he actually learned because he was a chemist. So David Reid was not an engineer, but he was a physician and a chemist. So he was a medical doctor, so he was interested in physiology, but he was a teacher, professor of practical chemistry in Edinburgh. And he was teaching essentially chemistry not only as a scientific subject in theory, as a theoretical subject, but also as a craft. So you learn the crafts of doing scientific experiments, but you also learn how you can utilize the experiments to address everyday problems. So we might call that today applied experimental research. And he outlined that in the various educational books that he published, which I've just listed here. I think this is really interesting because he eventually would link this back to architecture and arguing that actually this curriculum that he sort of outlined there for chemistry students could be appropriate as a model for reforming architecture education in the 19th century. And in this case, it was a move away from the overly formalistic education of architects and one that is more strongly founded in scientific methods. And I will show you why that is significant. And for Reed, and I think that is important to understand, and that's what I'm going to be talking about today, is the experimental phase of the House of Parliament. So those experiments that were done before the building went on site. And this is a period, and I've shown you in this is a sort of flow diagram that's been sort of developing as part of this larger project, is that we can see here Reed is starting off with his experiment well before he started actually getting involved in the palace proper. And this was 5 years after Barry's design was selected. This is quite important. So there were 5 years of development in the palace where Reed, as a ventilating scientist, was not involved. It was after 5 years that he suddenly was asked to apply scientific experimental research findings to the actual building. And this is really interesting that you have at this time a chasm between what we might call the sort of architectural development of the project and the scientific development of the project. And then there was a time when it was brought together again at that point. And at that point, a lot of challenges were encountered. So what I will be focusing on today is really that period here when Reed as a scientist was able to focus on experimentation independently from Barry's architectural explorations in the project. And this is sort of a picture, and this is sort of a picture showing the state of the palace as it was proposed originally in the competition, the Pugin and Barry. And what you can see, it already had towers, so the front towers and these were the architectural towers that existed, that were later adopted as ventilating towers, but they would also later add on all those spires I've seen you in the first picture. So the building was going through a transformation. But at this stage, so in 1835, the building was an architectural scheme where environmental considerations were rather of limited concern, and that was widely critiqued even at the time by the scientific architectural community. And we can see here, for instance, a block plan that was sketched at the time, showing that the building was actually believed to be like very quite a traditional approach of a courtyard-type house building where you would avoid deep planned spaces by putting courtyards in that would bring in light and allow also natural cross ventilation. So that was in 1835, that was the sort of traditional approach that was taken. At that time, there was no consideration of an actually stack ventilation system that was eventually adopted. So that is quite important to consider that actually with the adoption of the system 5 years later, a completely reinterpretation of the relationship between form and ventilation needed to be done. And it was in 1835, so when the design competition was opened, a separate select committee was appointed to look into the problem of ventilation, climate control, and acoustic and lighting as a sort of technical subject. And the belief was that these select committee could prepare recommendations that could later be applied once an architectural scheme had been selected. Because this committee met actually about half a year before Barry's design was officially selected, before actually the competition entries had arrived. So this was sort of going in parallel. So the beginning of that sort of technical separation from the architectural scheme started off with this initial inquiry. And as part of this inquiry, Reed was already invited, because the people were aware, the politicians were aware that Reed was actually already experimenting in Edinburgh with various ways of ventilating spaces using scientific methods. And he proposed a model debating chamber, which you can see here, which he believed was a sort of ideal form for a debating chamber. And this is what he presented before even an architectural scheme was conceived for the palace. He came up with this sort of ideal, what he considered sort of ideal form for a chamber. And the belief was that you could have a completely perforated floor here and the perforated ceiling where air would rise continuously from the floor through to the ceiling. Because the reason why this shape was adopted for acoustic reasons, because he believed that if the ceiling was lowered, it would be better as a sound reflecting panel. So that was his theory. And as a result, he was moving away from the traditional mode of having very tall buildings, so that you have a large volume of air in which you could breathe. In this case, he lowered the ceiling, the volume of air relative to the number of people in the room was reduced. In order to overcome that, he had this mechanical system driven by stacks, where air was continuously moving from the ceiling, from the floor to the ceiling. There was a continuous mechanical airflow through the chamber, rather than in the old traditional way having a large room where the windows were occasionally opened. So you saw that the way of reconciling the demand of acoustics with those of ventilation. So here this is a cross-section, just a diagrammatic cross-section that we produced for the committee, showing that they had actually proposed to use two chimneys. So there was one chimney where air was getting from a very high altitude down into the basement of the building. And there was a second chimney on the other side of the building that would have a ventilating fire here. So these stacks are not like modern advanced naturally ventilated building, which you might think of the Slavonic Studies building at UCL that Alan Short designed with these advanced ventilation stack, but this relied on heating, on coal fires to actually operate. So the heat inside these coals were driving the air out of the chambers, putting this essentially under a negative pressure and pulling air from the top of the chimney back down into the chamber. So this was a sort of mechanism. So there was we called it a vacuum, like a vacuum system, because essentially the hot air column rising to the top was creating a negative pressure that would put not only the chamber under pressure, but also the air passages here, and it would drive air from the top of the chimneys back down in again. So that was the theory. So it was purely one chimney driving the air quite long distances. So this was the sort of hypothetical proposal made in 1835, but eventually, because we realized that actually the committee embraced this and actually recommended this scheme, and, but it also asked them to test the system before it was applied. So what I want to show you in this diagram is that we got the situation now here where Reed actually, before he was invited to Westminster, had already experimented with a chemistry laboratory in Edinburgh that was actually inspiring this system for the Commons, where he had actually experimented with stack ventilation systems and was quite confident that you could use the same systems to deal with ventilating highly crowded debating chambers. So we have a period where actually the various structures were used. So before he was involved in Westminster, he had various experimental structures that he used to test his theory. But the committee neither did accept that actually his proposal, they were not confident that it would actually work and wanted to have further evidence. So what essentially happened is that that various sort of model debating chambers were constructed. So he had actually, before Westminster, he had already started with sort of room experiments. And they're going to show you some images of that in a minute, where he'd done a ventilation experiment with chamber, also again involving people. So he was not only looking at the technical performance, but also the physiological dimension, thermal comfort and air purity and so on. But then he designed a mock-up debating chamber in Edinburgh, where he first of all tested various of his systems, his ventilation system, the way he could integrate lighting, putting gas lighting into the system, and eventually would apply it to the temporary houses of Commons. And that's going to be the focus of today's talk. We're going to be talking about the importance of the temporary houses of Commons as the means of testing his model debating chamber under real life conditions with real people. And involving and having the actual parliament meeting in that model chamber was really significant. And I will show you, because it gave him that understanding of the system in a holistic way. So not only from a technical point of view, but also from an environmental, atmospheric point of view and physiological point of view. So we might talk about this as a sort of experimental phase of the building that eventually lead on to the actual design. And here we got an image of interior of the actual chemistry laboratory constructed in Edinburgh. And what you can see that the building consisted of various stacks. So it had the primary ventilating stack in the middle of it, and it had various auxiliary shafts lining the sides. So these functioned as chimney, but at the same time also as means of forcing air out of the building. And this was particularly important because it's just like a modern laboratory building. The challenge here was, how can you actually keep people safe in a space where you're dealing with highly noxious fumes? So you might think about Louis Kahn's laboratory building here, the highly serviced laboratory buildings here. This is sort of a 19th century incarnation of that. And he was really trying to use mechanical means of driving to get those fumes extracted. And so he had essentially two rather different strategies. On this diagrammatic cross-section, you can see that this is a large chimney I've shown you in the middle, which had also a ventilating fire at the bottom of the shaft, just as in this model debating chamber. But there were also pipes running underneath the floor of the laboratory, going to various chemistry benches. So it was a sort of fume extraction system where so this central chimney was essentially connected to a network of pipes that would withdraw fumes locally at the benches. And you can see here is a diagram that Reed himself produced showing those various experiments going on and the fumes being directly forced down into the shaft and out of the chimney. So that the fumes would only very little of the fumes would go into the atmosphere, but would be rather immediately extracted so that the students were safe. Because there were several hundred of these experiments going on at any one time, so there was a lot of fume being produced. And here's an image showing one of naphtha oil being burned and being sucked down, so the fumes being sucked down by one of these extract channels. So the system essentially had this extraction function, but here you can see these various ducts that were going underneath the floor. So this is actually an original floor plan showing how they're being conducted to various places. So this idea of a network of ducts driven by one central chimney and then complemented by additional side chimneys that were switched on under very extreme loads. And here is seen as an axiometric that I've produced that shows actually how these stacks work. And you can see there's the central stack that has these underfloor pipes, but it also has these louver openings here at various heights, which were about ventilating the actual atmosphere of the space. So it was a combination of fume obstruction and forcing the air out of the space. And here you can see again these louvers at various heights. And here you got a historic image showing these louvers that were for room ventilation. So there was extraction and room ventilation, all done with these stacks. So it was a mechanical power of these fires that were driving them. So these are not naturally, you shouldn't confuse these with the idea of a sort of natural ventilation stacks that are currently being sort of explored in modern building, but it's actually a sort of mechanical system which relied on these fires. And we did stress that very carefully, that actually the reliability was a main driver here. So in order to have a reliable extraction power, during this experiment was essentially critical to make actually his teaching laboratory inhabitable. Otherwise, the building would, at times, wouldn't be usable because of the level of fume pollution. So what we got is these stacks on the center, showing you here. This is the central stack here, and these are the auxiliary stacks. And then we got a temporary chamber, and that's going to be talking about in a minute, in size. And we can see there was actually a progression from very small stacks towards increasingly larger stacks. So these are stacks that were proposed for the actual Houses of Parliament, a much larger building. And I think just to keep in mind that there was a huge shift in scale of these buildings, of these towers, these ventilating towers. So in addition to its laboratory himself being an experiment, he also constructed various sort of mock-up model rooms where he experimented various ways of moving air through moving air in and out of sealed chambers rather than using natural ventilation through opening windows. He was seeing also a way of using a stack to forcing air artificially through spaces. And what he did, he explored various ways of perforating walls. So either in this case, he was perforating the walls and the ceiling to let air in and force air out. Here he experimented incorporating inlets and outlets at various different positions. So these were sort of mock-up models that he did inside his laboratory, connected to that chimney. So he was experimenting with ways how could be air artificially move through spaces in a controlled manner. So his interest was in creating very controlled environments, particularly in very crowded spaces. So what this led on to was this mock debating chamber. There was after his proposition in 1835, he built a relatively large-scale chamber that could be occupied. So he had actually a student there as subjects in the debating chamber where he would be doing physical, logical experiments, studying to see to what extent the air currents, because he was proposing to have air currents coming through the floor, he was also proposing ways of getting air through the ceiling, and studying to what extent that would have a physiological impact, because he realized that air currents could become rather uncomfortable if they were too strong. So he was sort of experimenting with that. At the same time, he was also finding ways of integrating gas lighting, which at that time comprised a lot of open flame gas lighting systems that would produce a lot of heat and a lot of pollution inside these rooms, unless they were isolated and very well ventilated. So what he did, he completely integrated the gas lighting into the exhaust system. So the heat of those, so they concealed those gas lights behind a glass screen that were in the corners of the space, and the hot air and fumes from these gas lights would exit at the same point as the ventilated air would do. So you saw that as an integrated system. And the heat would at the same time help to drive some of these airflows within the chamber. So to put this into scale, so this is actually a diagrammatic cross-section through the model chamber. What we see in orange is actually the temporary chamber, which was built for the actual Houses of Commons. And this cross-section shows the sort of proposed ideal chamber. So we have sort of different scales. So just to highlight, they were working in different scales. And again, there was this sort of emphasis on the three areas, how the performance of the system was looked at in a more holistic way. And then eventually, when he was sort of starting off, he was given the opportunity to actually apply the system to the temporary Houses of Commons, because Robert Smirke, the architect Robert Smirke, had actually fitted up a temporary chamber in 1834 after the big fire, so that the Houses of Commons could continue its business. This was within the ruins of the ancient Palace of Westminster, and this building became essentially the site for a major experiment on ventilating debating chambers or large lecture halls. And so this is the interior as it was designed by Robert Smirke, and in 1836 Reed was eventually allowed to modify the interior. And I just want to highlight that actually the Smirke building already had some actually ventilation system in place, but it was a very old-fashioned system that already sort of existed in the 17th century when they used heat sources in the loft space to force air through small openings in the ceiling and then let it out through the top. This has been experimented with in the House of Commons since the time of Christopher Wren. So that's always to make in mind that these systems of idea of using chimneys to forcing air out of it were not new. There were various incarnations of the idea that you could use heat rather than fans to drive air out of the chamber. So in Smirke's chamber, there were openings in the floor that could, with dampers that could be opened, and then you had these outlets at the top with these ventilating heat sources that would help them to draw air out at the top, while there were still various ways of opening windows to complement the ventilation. It was realized that the system was not at all anywhere effective, and that's why Reed was eventually called in, because they realized that these small openings and these small heat sources were by far not powerful enough to really draw air out of a chamber, where the flow rate needed to be quite high due to this high level of occupation. So this is actually an example here of a system that was introduced by Wren in the late 17th century, which didn't have fires originally, so there were just cones that were in the ceiling, and the belief was that hot air at the top would just escape through these cones. And then it was Jean Desaguliers who eventually in the 18th century would add a furnace to it, to power, to drive air, to assist the air to escape through these cones. So there was sort of this experiment going on, so the House of Parliament was not unacquainted with experimentation in this area. There was a lot of select committees throughout the years exploring various technical solutions, but not very successful. Here we see the interior of the Houses of Commons before the fire, and we can see here these openings. These are the openings through which the hot air was rising, and that's where the heat sources were above, in the ceiling above. And there was a chandelier here also with an outlet in the middle. And there were also other experiments with using fanners, and this time they often involved actually real people driving this ventilating fan. And you can imagine that being very fatigue problems prone. So eventually they will connect the steam engine to that to drive this. So this, but all these systems were not found to be particularly effective. So what Reed essentially did, so this is the interior of the new temporary house, and the Smirk's temporary house being converted, and you see the proportion had completely changed. He introduced this false ceiling, which had glazed sides where light would come in, and these would eventually be the glazing that would isolate the gas lighting. And they experimented various forms of lighting, because at that time no electric lighting was available, but lighting relied on combustions of either was candle, oil, or gas. So these were the primary fuels that were used. They were very prone to producing lots of fumes and a lot of heat. So there was a lot of experimentation going on in ways of isolating that from the main atmospheres of the chamber. And so if you compare the cross-section, you can see that he decided to seal off the building entirely from the windows. So while Smirk still allowed windows to be open at times when the system was not powerful enough, he decided to cover up the windows and have the building completely mechanically controlled in terms of the airflow. Here we can see these glazings again. Here the central panel where that was dedicated to the extraction of air. And this is a floor plan of the temporary. And so this is the old palace yard. So Westminster Abbey is also about here. So if you orientate yourselves, the old palace yard. So this is the House of Commons that we're going to be talking about. And what Reed essentially did, he built a big chimney next to the building. Rather than having a small chimney on the top of the building that wouldn't be powerful enough, he built a very large chimney next to the building, believing that that would be powerful enough to force air through the building without relying on any windows. So he developed this system of ducts that will run at the ceiling at the top. So you can see this duct here was essentially connecting directly to that chimney. And here you can see it more closer, and it was eventually also extended to the House of Lords, and I'm going to be explaining that a bit later, what's happening there. But it was sort of conducting this, so this idea was that you had a central chimney that you connect to various spaces via these ducts, and that the fires within that stack would extract the air from the top and would also force in air from these inlets. So there was no fan in the basement that would provide this type of plenum, for instance, that would drive in fresh air, but it was again the belief that us in this original hypothetical scheme that the chimney would be strong enough to drive the airflow in the building entirely. So this is an axiomatic that I've produced based on a historic evidence of that temporary chamber, because the original drawing of it actually have not survived, only very schematic sketches and diagrams. And what you can see from here is that this chimney was built next to it, but it was actually much more complex. So if you saw the diagram that Reed was drawing, there was a very idealized version. But actually what was going on here is that you had actually quite a complicated path. So you needed to take the air from the ceiling down through a tunnel to the shaft. And then these ducts that were conducted all the way across to the House of Lords as well. So there's something to keep in mind, that these systems were actually quite complex, and that was partially one of the reasons why the system was not as effective as it was intended, because it was a very complex path. So the fire had to work against the friction caused by the complicated air path. And what you also can see is that underneath the building, the entire air handling was done underneath the building, and they had a system where air was coming in through the bottom, and there were various filtration facilities, and I'm going to go into that in a bit more detail in a minute. But the air was essentially tempered before it got into the chamber, but the whole air came in from here. Was the power of this negative pressure produced by that stack that was believed to be powerful enough to drive air through this whole way. And here you can see a sort of close-up of it, how these ducts are conducted, the ventilating fire here inside the shaft, how the air was conducted through up. And so that's always something to keep in mind. And also just to explain how the system actually works, and I think this is always quite critical to just be aware that how the system was conceived, that we have actually various forces at play here. So if you imagine a situation in the summer when the heating was not turned on, we had primarily the chimney here that was giving the power for ventilation. So the fires here were putting this chamber under negative pressure. And this negative pressure would suck the air out of the chamber, but it also would force in air from the old palace yard through the basement and then through a perforated floor into the chamber. So at that time we might say the building was operating in a completely mechanical way. If the fires were turned off, the system wouldn't have worked purely due to the fact that the hot air would have just got stuck at a high level. It wouldn't have made its way naturally down the shaft. The result, as the tower was actually placed at the bottom of the chamber, made the system much more reliant on the fires than it would have been if you, as you find in many sort of advanced naturally ventilated buildings today, you would move it to the top of the building where the air would naturally progress towards. So here the fire was the way of overcoming that friction. You know, the air, the hot air accumulating at the top needed to be forced down the shaft to the bottom of the shaft. So this is what we might say the mechanical forces at play. But but in addition, within the chamber, so if we zoom in, we might think there's a lot of people in there, there's a lot of gas lighting burning. So within the chamber itself, you would have a stack effect emerging where there's a natural buoyancy of the heat from bodies and gas lights would create internal current that would also create a pool below. That would sort of enhance the negative pressure below the chamber, would help air to come in. So this would sort of assist at this stage some of the movement that the chimney would do. So there's always, and this in the winter when the heating was turned on, there was additional power given by the hot air that was provided in the mixing chamber below, would also help the air to move into the chamber. So there were these various different forces at play. So we're talking about the thermal current and the sort of mechanical current. The mechanical current being produced by the ventilating chimney. And it's also important to know that the whole building floor was perforated, and the belief was that you could actually distribute air and introduce it at every corner of the building. And you have got here the MPs were essentially sitting on a big sieve, on a metal grating. It was covered with a horsehair carpet. So the air was sort of, when you stand in the chamber, you would get these air currents rising up your feet, and that was commented on a lot. And the same was also at the gallery level. So the whole floor itself was a sort of a filter through which air was rising all the time and would eventually escape at the top. So there was a sort of continuous current rising through the floor, through to the ceiling. And just to understand that actually there was quite a lot of going on underneath the chamber. And this was the sort of idea that you could actually completely deal with the air, and that sort of, you could not only control the airflow, but you could also deal with the issue of air filtration, because London atmosphere was highly polluted, particularly from coal smokes and the various factories around Westminster. It was a highly polluted area at the time. So they had filters actually lining the inlet so that soot particles were eventually withdrawn from the incoming air. And then they had like types of shower sprinkler systems that would also sprinkle water over the incoming air in an attempt to remove those impurities in the atmosphere. At the same time, they helped to control some of the humidity as well as providing some cooling in summer. So this sort of system provided sort of a mixture of purposes. The air passage would eventually, so once the air was filtered and slightly cooled by the filter and the air, by the sprinkler system, they would go through various passages, and there was a way of controlling the air passages to create so the one where you could cool it by either passing cold water through the heating system, or in winter for heating the air by passing hot air through the heating system. So the air was a condition before it was actually moved into the chamber. And here we can see a floor plan. You can see how this was organized. So there were various stages, sort of going from one stage to the other before the air was achieved the state it was supposed to get. And we can see here's the inlets from the old palace yard with the filters, the sprinkler system here, and there were also blocks of ice occasionally hung up in the chamber during very hot weather. So ways of trying to control at that time the environment. And well, of course we have to remember there was no refrigeration, there was no air conditioning technology available at that time, so these were the technologies available to them. And you can see this system here where the air was eventually then allowed up to the chamber. And here you can see also in the floor plan the channel that would lead towards the extract shaft. So it's also important that actually Reed himself did talk a lot about the conditions in Westminster. There was a lot of problems with fog, and that's for this reason it was very important to seal up the building and to control the airflow, to filter the air before it was admitted. But he also made a reference, and I think this is important to understand the context of the 19th century, particularly 1830s up to the 1850s, that London at the time the environment was rather different from what we conceive it today, because this was a time of the Industrial Revolution, where there was a lot of pollution in inner city London, of a scale that we can't imagine anymore today. But what actually Reed was arguing is, because if you actually had depending on where you're building, you could have either a naturally ventilated building or a mechanically ventilated building. In this case, you refer to Hyde Park as a space where you could have a naturally ventilated building. It was rather on the fringes of London at the time, where it was less polluted. And this is quite important because so you can see here, this is Hyde Park, and this is where the House of Parliament is located, and this is an area where there was a lot of industry at the time, a lot of pollution. So it was in a very exposed location. And it's only that because Hyde Park was actually in this sort of more on the fringes of London, that something like the Great Exhibition, which was actually a building I studied as part of my PhD back in Cambridge, that was naturally ventilated without a sort of filtration system involved, without the use of a sort of mechanical conditioning system. This was possible because the pollution in that park was rather limited. So that is something to just remember in context. First of all, for Reed, then this experiment was not only limited to the House of Commons, but eventually allowed to also connect the system to the House of Lords, the temporary Houses of Lords, because they encountered problems with the ventilation. And what you can see in this drawing here is the transformation. So this was the original Smirk chamber. So this is what Smirk had designed, and this is what Reed eventually did. And you can see they put openings in the ceiling, for instance. That's where the second duct, the connecting to the central chimney, was located above those openings. You can see here the duct was extended to connect to the central shaft. So the system was becoming more what he considered a sort of network, a ventilation network. The House of Lords also became its own conditioning chamber, so the air handling chamber below was another one was provided. That was eventually also shared with the House of Commons, so they could switch between two different inlets. So one where sometimes the House of Commons providing a common inlet for the House of Lords and the House of Commons, while in other conditions there might have been the House of Lords inlet that was used for both houses. And this again was a response to pollution, so they could switch the inlet depending on where the pollution was coming from. So this was sort of theory that they were actually working together as a sort of system rather than as isolated ventilation problems. And here's a sort of diagram that we produced showing that he was actually thinking it more like a system of mains, and this time air flues that could be extended to almost any scale, and then you had a central chimney that would extract air wherever you need it. It's just a bit like in his laboratory in Edinburgh. And this is a drawing axiomatica I've produced of the actual House of Lords, and you can see these openings shown in the picture were actually leading into the duct above, and there were again openings at the benches below where the air was coming in. So a very different arrangement. No longer you had a completely perforated floor. And this was partly due to budgetary restrictions, because this again was only a temporary fit-up. This was only used to experiment, but he was allowed to now experiment the idea of, could I use a chimney to ventilate even two chambers at the same time? Because that's what he had in mind in the actual Palace of Westminster, one big chimney to ventilate several hundred rooms. Here in this case, it was only a handful of rooms and two debating chambers. So it was, again, a test bed for his ideas. Relatively small scale, but he could test them. And I've shown you this diagram again, and this is a duct essentially coming from the House of Lords across the House of Commons to the central shaft. So it was extending it quite substantially. And from that, so going back to the diagram, is that the building was, so there was not only this thinking going on in the actual design, but the building became also a major post-occupancy experiment. And this post-occupancy evaluation looked at these three areas in a great level of detail. And what is quite interesting is that there was a combination of essentially sort of four different ways of evaluating the building. And one was to look at the technical performance of the building, so the engineers coming in and seeing how the system was performing. Then there was a routine measurement of the environment, so the actually attendants of the ventilation were actually recording the temperature outside the building on a regular basis at hourly intervals during debates. So there was a lot of data was gathered about the actual temperatures inside the building, about the position of dampers, and how effective that was in terms of regulating temperature and airflow within the chamber. And then there was a lot of accumulated experience with the management of the system under different climate conditions and also with different levels of occupation. But what was mostly important is that actually there was also this concern about the feedback. So this system was not only that they were taking these measurements and following orders of the technicians, but they were involving the users of the building to feedback on their sense of thermal comfort, their perception of air quality in the chamber, and that would be used as the feedback mechanism for the attendants. The technicians not only followed orders, but they also took into account feedback from the user at all times. And there was a system set up. So what is interesting is that they actually did a performance study of the shaft on a technical level. They found, for instance, that the shaft performance varied quite a lot, depending on the season. In particular in the summer, there was a real trouble getting the shaft producing the power it needed. So so there was one problem. At the same time, they also had the problem that the shaft was by far not efficient enough to simultaneously ventilate both chambers, particularly when they were very, very crowded. So these were a very quite interesting experience. So what they did, they switched essentially the chimney from one chamber to the other to increase the power periodically in the various chambers, just to ensure that more ventilation was available when it was most needed. So there were these sort of technical experiences that eventually led Reed to actually develop a much larger chimney for his buildings. But it also highlighted the potential technical pitfalls that he might encounter with his vision. So in this diagram, I just want to show you that actually after the chamber was completed, there was a continuous post-occupancy evaluation going on over a period of 15 years. And there were various select committees that were appointed to inquire into various aspects of his technical performance, so lighting, ventilation, thermal comfort, and so on. So there was an enormously thorough investigation into, and that involved various scientists, external scientists, sometimes to do independent examinations. And because this chamber was quite in the media at the time, there was a lot of rumor whether, even among the MPs, whether Reed's system would actually really work in practice or whether it was rather a risky experiment. And Robert Smirke himself would continuously remind them that he didn't really trust what Reed was proposing. So what he did a public demonstration of his system where the media was present, various MPs as well, and he filled up the rooms by getting 420 grenadier guards into the space, as well as 150 gentlemen. So he got the chamber very crowded to just make his case. And through this demonstration, which took about an hour-long experiment, the media then reported, for instance, that the temperature inside the chamber didn't rise to very high temperature. It was, for instance, reported despite the number of people, it was only rising by 2 degrees Fahrenheit over the 1 hour they were in the chamber. Given the number of people in there, that was quite an achievement. And then to even demonstrate it more clearly to the audience that the system was very powerful, he ignited some gunpowder smoke into the atmosphere to show them how quickly that smoke would be evacuated. And there is this smoke, this quote, where they're sort of describing that the chamber filled up with the smoke, and it was so dark that you could hardly see the people opposite in the chamber. But it would only take really not that long for the chamber to be cleared again. So these were all sort of like public demonstration, very common in the 19th century in the scientific area, to demonstrate it through real-life demonstrations how effective the system was. And this was reported in the media and got the media a bit calm about the sneering that was going on before. So in addition to that, there was this sort of first experiment, but actually the chamber was monitored continuously. And this is just showing you an example where the thermometers were placed. So what they essentially monitored was temperatures, dry bulb temperature. And they had these thermometers placed inside the chamber itself, where it's very often about a feedback about thermal comfort, about the temperature ranges that occurred there, but also the temperatures inside the mixing chamber and the exhaust shaft. So they were keeping an eye on the temperature inside the building continuously through debates. Here you can see those logs were taken at hourly intervals in those various locations. They also plotted the number of occupants against that. So because there was a huge fluctuation, sometimes you had several hundred people in the debating chamber during very major debates, while at other times it dropped down to like only 40. So in this case it was 800 maximum. In other cases it was 40. So there was a huge fluctuation. So the system needed to cope with that. And there was very often a matter of performance management. And this performance management was also quite a lot of coordination. So there were various systems in place that allowed them to make the recording of temperature more convenient, developing systems of getting thermometers down to the attendants through mechanism. But what is quite remarkable is that through that they gathered an enormous amount of data about the actual conditions inside the chamber. And this is a typical day, and this is May 1837. Just to show you one sample of the data that was collected, and what you can see, for instance, here the temperature above here are the temperature that are actually in the chamber that was occupied, while then you got here the fluctuation in the number of people in the chamber. So you can see there's a huge fluctuation in the number of people, while the temperatures above, you can see, did stay relatively stable comparatively to the magnitude of change. And this was the sort of evidence that was required on one level to demonstrate that actually this idea that Reed had was actually working reasonably well. You can also see operations down here, which is the damper opening. So they were recording the size of the opening of the dampers at any one time. So you can start plotting that against the number of people and against the temperature. And you can see the sort of relationship, how the system was actually managed in response to occupants' change. It's the same thing they recorded the external temperatures. And here is a sort of close-up, and you can see here these temperatures that are within the chamber. You can see there's sort of slight variation because some were higher up in the space. The galleries was generally hotter than it was at the main floor of the debating chamber. Here's a sort of another sample of sets, and again you can see the temperature ranges in the chamber stayed really comparatively stable given the fact that there's a huge fluctuation in the number of people. So you can see that from that point of view, but this of course was not the only aspect that had to be considered. And here again we've got a winter scenario, so a sample of some data was collected in the winter. And again the similar phenomena, the temperatures didn't change as radically as the number of people. And there was a sort of routine operations. I'm not going to go into this detail, but it's important to know that there was a routine that the management was following of what type of temperatures, how the system was to be so operated under different weather conditions, under different levels of occupation. So I had this sort of winter and summer control regime that they had to sort of as a guide for them to follow. And this was refined through experimentation. So there was an initial one, but was eventually refined. And this refinement led them also to continue elaborating the monitoring and introducing more and more data to get a more and more refined understanding of its actual behavior. And this is sort of a more extended form that eventually was adopted in the actual permanent Houses of Commons that was opened in the 1850s. But what is also actually important to really is to remember that people at the time saw the building as a rather sophisticated enterprise. Managing a building at the time without computer controls, without automatic sensors, required a well-organized team that was very, very, very disciplined. So they took this analogy of a sailor steering a ship. somebody who knew really well how to steer a ship through a very difficult weather. And that sort of empirical experience of how a sailing ship behaves under very different weather conditions, and depending on the state of the waves and so on, that sort of level of intimate understanding was gained by the management as they observed. So it was very much experiential. So the management of the system, so they had these thermometers that gave them feedback, but they also made direct observations. So there was a lot of sophistication. That's something that we forgot today, because the computers do sort of hide in some way the reality of some of these very sophisticated systems that required a lot of smart controls. Here we got some examples of data collected by attendants in the permanent Houses of Commons. In this case, a period from the 1843 to 1928. So a huge amount of data was collected that included not only temperature reading, but also various commentaries. So experience they were making as the system was not behaving as they were anticipating. So it was a accumulated experience. Here you've got an example of these manually logged temperatures. So no tiny text as those days, computer logging. Again, here comments on various experiences of MPs within the chamber that was recorded by the attendants. It's quite important to know that the attendants were quite aware how the people were feeling inside the chamber. Here again, some operational recordings with various times being plotted against it. But I think if you sort of look at this as a whole management process, I think it's very important that actually at the time they were realizing that actually to manage the system they needed to get the user on board, to get the satisfaction, because they were aware that there's actually a difference between what you might sort of call the ideal temperature you want to achieve, and that what people see as satisfactory. So people feel comfortable rather than expecting everybody to feel comfortable in the same conditions. And this was found to be a major driver. There were lots of complaints going on in the chamber about the conditions. And this put Reed under enormous pressure, even in the public, because a lot of the MPs would actually write in the newspapers and agitate against him for that reason. So that perceived thermal comfort was rather critical, and this became a political matter for him. So what eventually evolved from that is to have a sophisticated management system, which this diagram illustrates, is that you not only had the routine managements that I've just explained with the temperature logging and so on, and the routine operations that were followed, but they also had the system in place that took into account the user feedback. So the sergeant at arms himself was actually in charge of consulting users about how they were feeling about the temperature, how comfortable they felt that way, and how they were happy with the air purity. So there was a very subjective element in the operation that was taken as a measure for evaluating its performance. What the sergeant at arms essentially did is passing on that feedback, which of course he had to filter. He had to negotiate with the MPs across, because there was a lot of disagreement among the various MPs about who felt comfortable and who not. So he had to come up with a sort of some degree of negotiation and come up with some sort of consensus about how comfortable. So it became a sort of political thing in its own right. So this information was eventually then the filtered information the sergeant at arms essentially passed on to the chief attendant of the system, who would make ad hoc changes according to those feedback. And that feedback eventually would then again fed back to the sergeant at arms to see how effective these changes were. And this is quite important, because in terms of the human element, the system really built the user in. And this, of course, in the 19th century is very different from modern ideas of user-centered environmental strategies that are sort of currently being investigated quite a lot. Is, how can you actually have a system that takes into account individual preferences, rather than assuming there's being a one standard for all. So in this system, that was actually already taken into account. It's quite remarkable. This is Sergeant at Arms himself commenting on experience. And this is quite humorous, to know how actually that experience was a Sergeant at Arms responsible of actually getting people to agree on something. In this case, even if it's something about how comfortable they felt. So they had people who felt hot, other times they had people at the same time feeling too cold. There was a rather difficult negotiation going on. There were other phenomena again, was found that actually even over time people's sense of comfort changed. So when there were debates going on and they were very heated, people felt rather very hot and they had to lower temperatures. So there was a lot of change. So the building was continuously adjusted in according to the changing conditions. And I think it's also important because of the wave of criticism, Reid himself needed to actually go in to the House of Commons and get MPs to write testimony about their satisfaction with the system. The negative press was getting so fierce that he tried to counteract that with publishing in the media some more positive accounts by major figures in the Houses of Commons. This is really it became a sort of thing that was actually on the letters page. There was a lot of going on this on the letters page of the Times, for instance, at the time. And there was sort of eventually, because of these complaints, and of course not all of these complaints, of course, was just a matter of personal preference, but there were also really major technical problems from a physiological point of view in particular. And that's why it's really quite important to realize that this was not only a technical issue, but it was also one of human physiology. And what was observed in the study that Reid was eventually done in December 1837 is there was a problem with dust rising in the chamber and excessive dryness in the atmosphere. So there were things that were actually not measured. So the thermometers were only measuring air temperature. It didn't take into consideration either the humidity, the relative humidity in the chamber, nor did it take into consideration the thermal sensation of air currents coming through the floor. And these were the things that people complained about. They complained about having cold feet and hot heads because the strong currents coming through the floor made their feet feel rather cold, while their heads were rather warm air. So these sort of problems, equally there were problems with the air quality actually causing problems with headaches, because there was no way of actually systematically recording, for instance, the CO2 content of the atmosphere or any other form of impurity in the chamber. They really relied on direct feedback, and this direct feedback very often led to a state where people felt rather uncomfortable because of the state of the atmosphere. But so these were the sort of main physiological problems that were encountered. And there were sort of various investigations made into the problem of that. For instance, the stratifications of hot air, that the galleries were always hotter than the main floor. And they did various experiments where they show, and actually there was sort of a problem with there was believed to be a problem with the extract. So they did some gunpowder experiments to check actually how much air was actually now moving through the chamber after that one big public demonstration. And that time it was actually felt that the currents were not strong enough at times. So that the system was not always performing as well as it was originally demonstrated. And here you can see some of these sort of stratification data that you had a sort of variation of 3 to 4 degrees Fahrenheit between the top and the floor of the chamber. And this very often also informed that sort of disagreement that people on the galleries felt too hot, while those at the bottom sometimes feel a bit rather cool comparatively. And it's just to highlight that the floor being perforated, so the whole floor itself was a big sieve, and this where all these currents came through. And as a result was that there were various problems. Chill, so the main problem with the chill coming through the chamber was explored, and remedial action were attempted. And these are sort of experiments that were done where they were trying to get air from the ceiling rather than through the floor in an attempt in order not to expose people to the incoming air current, so it would be coming in from the ceiling rather. They made various experiments with covering up the floor and only letting the air through the floor at various places in order to address that sort of physiological dimension. And that physiological dimension would also eventually form various modifications implemented in the permanent Houses of Commons. And one of the problems, for instance, was actually found that actually sometimes the air rushed out too quickly out of the chamber. They blocked off some of these openings, which at the time caused problems of air not being extracted efficiently. So what it was actually coming into is that there was a belief was that actually Reid himself could just through ventilation keep the temperature at check. But what was found out is by powering up the chimney is that this current became the main cause of discomfort rather than high temperatures. And as a result of that, they were attempting to make experiments with cooling the air, with actively cooling the air, which was something that was actually not really possible at the time. was very, very difficult. So they experimented with actually introducing ice in the chamber to cool the air before it came in, rather than having to have strong air currents coming into the chamber. So this is sort of quite important, that actually this idea that you could use currents to keep the temperature in check had also a physiological side effect, because the air current that were not measured were reported by the people. So the subjective feedback did pick that up. And I think this is sort of important, that actually as a result of that, Reed in his, this is a diagrammatic cross-section of an initial proposal done for the Palace of Westminster, so the actual ventilation system that Reed originally had in mind, which is not the one that was actually implemented, where he had this idea that you could actually provide a cool air reservoir underneath the palace to cool the air, so that you would no longer rely on these very strong currents to lower the indoor temperature. So the idea of having a cool air reservoir within the basement to counteract some of these physiological problems, as cooling at that time was incredibly difficult to achieve and enormously expensive. So what essentially another scientist did a study on that chill current, and he realized that actually that these air currents were actually causing enormous chill effects on people's skin, even when the chamber was actually rather hot. And he reported that the temperature could be as high as 80 degrees Fahrenheit, but people felt rather chilly because of these currents. So that's really interesting in terms of this sort of physiological understanding that was actually gained in that context. And he realized that dry bulb thermometers were not appropriate, but that you needed to have thermometers that could also take into consideration the relative humidity of the chamber, so that the excessive dryness that was reported could also be measured. So there was always this sort of element of what was actually quantifiable at the time, because one needs to always keep that in mind, that the scientific means available at the time to measure air quality was very, very limited. And that, as a result, it was not only that you needed people to report on the environmental conditions because it's about the subjective experience, but it was also necessary because a lot of elements were not measured, could not be measured, or at least not very easily, and not at regular intervals. So what Gurney was actually, the Gurney as a scientist was indicating is that actually we need to, what is measurable should be extended. In this case, he was noting that there are thermometers around that could actually measure relative humidity and therefore cover more of what was measurable. And I think we need, so I think this is sort of really, I want to sort of, as a sort of concluding slide, want to illustrate that these experiments were part of the beginning of an scientific experimental inquiry going on in the palace until really the Second World War, is where they are actually extending the sort of monitoring of the environment. So what could actually be studied became more and more. And you can see, for instance, we started off with the temperature. Eventually they started measuring relative humidity in air currents. But by the latter part of the century, when they were developing more advanced techniques of chemical analysis, they would also take chemical samples of the atmosphere and see what the chemical composition of the atmosphere was. So these were techniques that weren't that available to read at the time, but it became available over time. So what was happening is the building became more, the monitoring became incredibly more sophisticated over the century, and the more detailed understanding of what was actually happening in the chamber in a more quantitative way could be achieved. So eventually it was a bacteriological analysis, so you could actually see what the bacteriological state of the atmosphere was. This was particularly in the context of the River Thames that was highly polluted at the time. It was believed to be the cause of a lot of diseases. So it was really quite an interest to see how pure from a bacteriological level the atmosphere was. So what essentially was previously, a lot of this was either unknown, so bacteria were actually not known under Reed's time, so it was not actually visible, so it could not be measured. But this time it became a factor that could be measured, and that was understood. So there was a sort of relationship between developments in the sciences and monitoring technology and the level of understanding of the chamber's performance. And I think that's a sort of, this sort of puts into context really how technologies in the 19th century were actually in some ways in their thinking far ahead of their level of knowledge. This idea that you could have actually a system where for the whole environment was subject of quantification and monitoring. In this case, at the beginning, they really needed to resort on people as forms of indicators rather than having instruments. I think this is sort of quite critical, because through that, they would eventually get a much more profound understanding of what they were actually doing in the chamber. And that's where I would like to leave it today. And I hope I've sort of given a sort of clear overview. I mean, this was really about the sort of experimental research that was going on in the chamber and how this was sort of used to gain a real performance understanding of building. This is not very dissimilar from what we're doing today, where we still rely on actually doing post-occupancy evaluations of buildings, of energy efficient buildings or highly advanced naturally ventilated buildings, to gain an understanding of the actual performance and also to improve their management. Because these feedbacks, these were all part of a feedback loop that allowed the management to continuously refine the management, as well as gaining an understanding of actually what was going on in the chamber.
Thank you very much, Henrik.